Okay, there we go. So yesterday we introduced a number of important ideas, or a number of important ideas related to ideas, or another important aspects of ideas that we need to consider if we're going to try to explain where ideas come from. The first is this idea of non-rivalry, that ideas can be used by many people at one time. And so what that does is that creates a lot of positive externalities, right? In other words, when somebody creates an idea, it doesn't just impact them, it impacts other people around them. And so this is one of the reasons why ideas have such power, right? Is that ideas just don't impact a small number of people. They have the potential to impact a large number of people because of their very nature. As we talked about that quote from Thomas Jefferson, that ideas are kind of like taking a candle and lighting somebody else's candle, right? You give them light without necessarily eliminating any of your own. As a result, ideas leak and they match. Ideas create a lot of leaks in the sense that when I have an idea, it has some impact on you. When you have an idea, it has some impact on me. Ideas also match in that my idea and your idea, when we put them together, we often come up with something that's much bigger than the sum of our two ideas, right? And so the fact that we have all these positive externalities and all these leaks and matches really point to the fact that networks are crucial to the creation of ideas, right? Ideas are rarely created by one single individual or even small groups of individuals, right? Most ideas tend to be networked, meaning large groups of people who kind of contribute in small but cumulative ways to the creation of new ideas. All of this stuff is great about ideas, but of course there's also some problems with with this conception of ideas, right? These are all positive things from the economic perspective about ideas, but then there's some also negative economic impacts of ideas. One of them is as we talked about, is the problem of free riding. Because ideas leak and match, that does minimize the incentive to create an idea yourself. Because what you can do is you can try to free ride off of other people's ideas, wait around for somebody else to make an idea, and then you can just use it. And as we talked about yesterday, that's one of the arguments for having patents, right? Is that patents prevent people from free riding and allow you to kind of create the benefits of any idea you create. Another big problem with patents, I'm sorry, another big idea, another potential problem with ideas is that they often involve a lot of fixed costs. So ideas will not get created unless you create incentives or ways for firms to pay off the fixed costs of their big ideas, right? So once again, there would likely be very few um, pharmaceutical ideas created if we didn't have a world of patents. Why? Because creating a new pharmaceutical is so expensive in terms of its fixed costs. So if Pfizer spent billions of dollars developing a pharmaceutical, developing a vaccine, and then immediately anybody could make a knockoff version of that vaccine, it would be very difficult for Pfizer to ever cover its fixed costs. And so it's not going to make those vaccines in the first place. And so once again, fixed costs are one of the important reasons why we have patents. But while a patent might allow you to cover your fixed costs, the problem with a patent is that it creates imperfect competition. Okay, it creates imperfect competition. Meaning that we tend to get monopolies in any industry that is very ideas focused, right? So industries that tend to be heavily weighted toward the creation of new ideas also tend to be imperfectly competitive, oftentimes monopolies or monopolistic competition. Okay, so that's just a very brief review of what we talked about yesterday. And so, I think the key takeaway from this is that it's very difficult to think about the creation of ideas in the same way that we think about the creation of corn or furniture or really almost any other good within an economy. Ideas are fundamentally different from most goods in an economy, right? And so their creation is messy, right? It's complicated and it's messy. And the economics of it are quite complicated because we all know that ideas create all these positive externalities, which is good. But then we also know that all these ideas create negative externalities in the form of imperfect competition and potentially monopoly. And so, how exactly, as a society and through policy, we are supposed to regulate the creation of ideas, is a very, very challenging one, right? And so, without getting too much in the weeds on this, I have to say that one of the more interesting topics among economists is, like, for instance, what should patent law look like, right? That's actually a really fascinating topic because there's just a lot to consider. On one hand, we need patents because firms need to be able to cover their fixed costs, right? But on the flip side, patents create a monopoly and they also prevent leaks and matches. So how do we balance those things, right? How do we create law and policy that both helps incentivize firms to incur the fixed costs to invest in these important ideas, but also then how do we make sure that once these ideas are created, we are not just held hostage by monopolists, right? And so, as we said yesterday, these kind of arguments seem particularly pressing and relevant today when we're having this big discussion about social media and technology companies, right? Like Google, Apple, right? How much power should these companies have? They seem to have an awful lot of power. Now, on the flip side, they create an awful lot of ideas. So how exactly do we balance the positive externalities created by a company like Google versus the negative externalities of a monopolist like Google, right? And that's not even getting into any of the concerns about privacy and who owns the information about you and all this. I mean, the economics of all this are really complicated, but they're actually quite fascinating. Okay, well, in this class, we're not going to get into the details, right? Remember, our big focus here is what creates growth? What creates growth in an economy? So when we talked about our simple model of production in chapter 4, and we talked about our solo model in chapter 5, we learned that aggregate productivity is the key to increasing standards of living and the key to increasing growth. However, neither of those models had anything to say about where productivity comes from, where technology comes from. And so we would like to have a model that actually helps us think about that, right? That helps us understand that. And so that's the Romer model. Okay. So let's talk about the Romer model here. What is the Romer model? The key to the Romer model is we want to endogenize A, right? In other words, we want to try to explain where increases in productivity come from. So in this model, we're going to see that ideas are produced through research and development. So firms not only produce not only produce output, but firms also can choose to produce ideas. How do they produce ideas? Through investment, not in capital, but in research and development. Okay? So we're going to see a model in which really firms have two production functions now, one to produce output, the other to produce ideas. The key, though, here is that these ideas are non-rivalrous. Right? They're non-rivalrous. They create economies of scale. And these together lead to a growth in A and a growth in per capita GDP. Okay. So that is, in a kind of from the highest view, right, the high level view of the Romer model, this is what the Romer model is trying to do. It's trying to explain why A grows over time. And why does A grow? The focus here is on research and development. Firms spend money on research and development. Research and development creates new ideas that create lots of positive externalities. These positive externalities then lead to growth in A and growth in per capita GDP. Okay, so let's develop the model here. And as always, the model is really its assumptions. So what are the assumptions? Okay, we're going to make this model very, very simple. We're not even going to include physical capital in this model. All right, we're going to make this model very, very simple. It's relatively easy to put physical capital in this model. In fact, the appendix to chapter 6 does that. We might talk about how the model changes a little bit if you put capital in it, but at least on the first pass here, we're going to keep this very simple. So first assumption is we have a production function for output. Right? What's our production function? This, right? So we're going to assume no capital here. We're just going to ignore capital, once again, to keep this very simple. What's LYT? It's output devoted to labor. I'm sorry, labor devoted to output production. Because as we're going to see in a minute, some workers are going to work at making output, but some workers are going to be devoted to creating research and development, right? So some workers are going to produce output, some workers are going to produce ideas. The workers that produce output, LYT, right? So here's our production function for output. Very, very simple. And once again, it looks a little weird because we've dropped physical capital from this, but that's an easy enough thing to add in later, but right now we'll keep things as simple as possible. Now, here's where things get a little different. Not only do we have a production function for output, now we have a production function for ideas. What does this production function for ideas look like? This is the equation that really is the workhorse, right? Here's the cornerstone of everything that's going on in this model. So it's crucial that we understand this equation if we're going to understand the Solow model. The production function for ideas simply says that the change in AT plus 1 is equal to Z bar times AT times LAT, right? What's LAT? This is labor devoted to research and development. Okay, labor devoted to producing ideas. Z is just an exogenous variable, right? You can kind of think about this as exogenous productivity in producing ideas. By including Z, we're allowing ourselves the possibility that sometimes a country could get better at producing ideas or could get worse at producing ideas, right? But the key here is that this is exogenous, right? We're not trying to explain where this comes from in the model. Now, what in the world is this equation saying that we have AT on one side and delta AT plus 1 on the other? Well, this is really getting back to what we talked about here in my preamble. What's the key to producing ideas? Having ideas, right? The more ideas you have, the more ideas you produce. Hold on. Sorry, shoot, something has frozen on my computer. There we go. Okay. Okay. So remember, ideas are the change in technology, or the change in our productivity. So we can think about delta AT plus 1 is ideas, right? Right, the new ideas. While AT is the stock of existing ideas. So what this equation here is saying is that if you have more existing ideas, you will also produce more new ideas. Okay? This is really at the heart of what we were talking about. I was just talking about in a couple minutes ago, right? This is at the heart of leaks and matches and positive externalities, right? What's the key component to producing ideas? Having ideas already. The more ideas you have, the more ideas you produce. This helps us understand many of those facts that I talked about yesterday. Remember, I showed you some data that suggests that ideas are produced in a very small number of areas where there are more and more people, right? That's consistent with this, right? Where you have more people and where you have more ideas, you will produce more new ideas, right? So most patents are produced in what, I think 20 urban areas across the globe, right? That's consistent with this. The more ideas you have, the more ideas you produce, okay? So this is absolutely the cornerstone of this Romer model, right? That's the cornerstone. That's really where we're gonna get growth, is by producing ideas, we will create more ideas, and that's what's gonna drive growth, right? So everyone kind of get the intuition behind this equation before we go on, because, you know, like I said, everything else is going to be really kind of be built upon this. All right, the rest of the assumptions are really just kind of finishing out the model, right? Just kind of closing it off. We're going to assume that the labor supply is fixed. So we're not going to have population growth in here. And so what is the labor supply? It's L bar, and here you either have to work at producing output or you have to work at producing ideas, right? So some people work at producing output, some people work at producing ideas. How do we decide who produces output and who produces ideas? Well, in the real in the real Romer model, this is actually endogenous, meaning you actually can have firms trying to maximize profit will make a choice between how many workers they want producing output and how many workers they want producing ideas. And notice here, there's a trade-off for firms. If they decide that they want to produce more ideas, they get less profits today because they produce less output. So there's a trade-off here for firms. And so in the real adopted Romer model, firms kind of, maximize profits and make this choice. That gets a little complicated in terms of the math of it. So we're just going to keep it, once again, very simple. And we're just going to assume that a constant fraction of the labor force is devoted to producing research and development. Okay, so we're not going to make this endogenous. We're not going to really explain this process in the model. We're just going to make it exogenous and assume that this is true, where L bar is the exogenous fraction of the labor force working in R&D. Okay, so once again, the key here is to keep it simple. And so we're just going to assume that this is exogenous. Maybe not the most interesting or realistic assumption, but we're just going to work with this. Okay, that's really the model, right? That's the simple Romer model. So let's, just as a recap here, let's make sure that we know what our endogenous variables are. And what our exogenous variables are. So the exogenous variables are pretty easy. If we go back and we look at the variables that have the bar over them, we have Z, right, which is our productivity parameter. We have L, which is the fraction of people devoted to research and development. And then we have the labor supply. And what is endogenous? Y, LYT, LAT, and most importantly, A. And that's really what the Romer model is trying to do, right? We're trying to explain where A comes from. We're trying to endogenize A. All right, you all with me so far?
Quick question.
Yeah.
Is there times that labor and then the idea are lowercase l with the bar? Is there any exceptions when they're considered the same or not at all? Like if there was a company that, like a think tank, when that's their sole purpose?
Mm-hmm. Well, not in this model. I mean, I agree with you that in the real world, the distinction between producing research and development and producing output or a service is not always so clear, but not in this model, right? We're trying to keep things simple in this model. So yeah, in this simple, we have like a clear dichotomy between producing ideas and producing output. But I agree with you, Cole, in the real world, yeah, there's not always such a clear distinction. I don't think, though, that necessarily changes the conclusions of this model, right? I think if you added something like that to the model, I don't think it's necessarily going to change some of the basic insights of this model that we're going to get to in a couple of minutes. All right, and maybe I'll come back to that and explain why I don't think it's going to change many of the basic insights. Okay, so let's talk about what this model means. Let's begin by rewriting the model in per capita terms. Right? So per capita output, lowercase y, is equal to capital Y divided by L. And so if you remember, what's capital output? Anybody remember? We go back here, scroll back. It's this, right? However, we know from assumption 4, that what is LYT? It's equal to that. And so, plugging in, that's what per capita production function is. Okay. So what determines per capita output in this model? Aggregate productivity, but also 1 minus L. So let's think about this. If you increase L, little l, sorry, the number of people that you have working in research and development, does that increase out per capita output or decrease that per capita output? It's going to depend, right? Because notice here that if you increase L, that also increases A, which will increase Y. But of course, that also reduces 1 minus L, which reduces per capita output. So spending more on research and development is going to have an ambiguous effect on output, right? It's going to have an ambiguous effect on output. There's a trade-off here. There's a trade-off. And I think if you think about this, this makes a lot of sense, right? Should we as a society send everybody to a PhD program so that they can run research labs? Well, probably not, because we also need somebody to be producing output for the here and now, right? And so when you devote more workers to research and development, yes, you're going to increase A in the long run, but in the short run, you're going to reduce output because you're going to have fewer people working, okay? And so this per capita production function captures this trade-off. Can you guys hear my dog snoring? Okay, good. I don't want it to distract you. My dog is sitting here on the ground doing some weird ass snoring. So anyway, if you hear some bizarre sounds, it's just my dog. All right. So so that's the per capita production function. Now let's go back and rewrite the ideas production function. And how I'm going to rewrite this as, let's divide each side by A. Okay? So divide each side by A, and then we can also simplify this, noting that what is LAT? It's that. What is this over here? This is the growth rate, right? The change in A divided by A is a growth rate. This is the growth rate of ideas. We'll often refer to this as G. Oops. Okay, your book often uses, refers to this as G. And notice in this model that the growth rate is actually exogenous because it's really the function of three exogenous factors. Ideas grow faster when first Z bar is higher, right? We're essentially better at making the ideas. And that's what Z is capturing, right? The exogenous factor that kind of captures how good we are at making ideas. The second thing is L bar, right? When L bar goes up, little L bar goes up, this means that we're devoting more people to working on research and development, right? So more people producing research and development. That also is going to lead to an increase in the growth of ideas. And third, and this is going to be one we're going to talk about here more, because this one is going to lead to a direct contradiction of something that a prediction that was in the Solow model, is having more people leads to more ideas. So in the Romer model, the more people you have, the faster you should grow, because you're going to have more people to devote to producing ideas, right? The more people you have, the more leaks and matches you have, the more ideas you get. So the Romer model actually predicts that as population gets bigger, you should actually get richer, not poorer, right? And if you remember yesterday when we talked about the Solow model, we talked about Malthus and this idea that more people means that you have diminishing margin returns to labor, right? And so more people means that people will get poorer over time. That's not the conclusion that we come to in this Romer model, right? More people means more ideas. We should actually get richer over time if we have more people. So G bar here is the growth rate of ideas. To put this another way, if ideas are growing at the rate of G, then there's exponential growth in A. In other words, what is AT? It's just an exponential function, just like we talked about on the first and second day of class. That what we get here is A is growing exponentially. So we're getting exponential growth in ideas at a constant growth rate. What's that constant growth rate? G bar. If we plug this into the production function, that we developed earlier, remember, we get this. Right? So if you remove AT from the earlier production function and plug this into the earlier production function, we get this. And what do we see here? We're getting exponential growth in YT as well. So in this model, we are not getting a steady state. This is not the Solow model, right? This is not the Solow model where we got a steady state in the long run where we didn't grow. Now we are getting constant growth forever. What we get here is what you might call not a steady state, but you call it a balanced growth path. What we're getting in this model is a balanced growth path. Okay, we're getting constant growth over time. So think about what this looks like. What is YT looking like? It's basically exponential growth. At the constant growth rate of G bar. So if this growth rate is 2% a year, using the rule of 70, right? Let's kind of plug this in. Let's say if we began at the constant, or we began at per capita growth of 2, right? So let's assume here that Y0 is 2, and let's assume that G bar is 2%, okay? Using our rule of 70, if it's growing at 2% a year, it means that we're going to be doubling in size every 35 years. So when we get to 35 years, we'll be at 4. And when we get to 70 years, we'll be at 8. And when we get to 105 years, this is obviously not to scale, we'll be at 16. And when we get to 140 years, we'll be at 32, right? We're having exponential growth that's growing at a compounded rate that's exploding in levels over time. If we put this on a ratio scale, then what's it going to look like? It's just going to be a linear line, right? Where we have 2 at times 0. Oops. Shoot, I'm sorry. I screwed this graph up. Try again. Okay. You have 2 at times 0, and then where are we at year 35? We're at 4. And where are we at 70? We're at 8. And where are we at 105? We're at 16. This is kind of a sloppy graph. Surprise, surprise. Right? And this becomes linear. So notice here that if I make the vertical axis not units, but ratio, right, where I double, every click is a doubling, I turn this into a linear relationship. So once again, the key here is that having ideas creates more ideas, right? Having ideas creates more ideas. That's what leads to long-run growth. It leads to long-run sustained increases in A, which then lead to long-run sustained increases in per capita output. Once again, where does this idea that ideas create more ideas come from? From the fact that ideas are non-rivalrous. They create leaks and matches and economies of scale that create all sorts of positive spillovers that drive growth. And so what we get in this model is we don't get a steady state like in the solar model, but we get a balanced growth path, right? Where we grow forever at a constant rate. All right, so that is the Romer model, right? That is the Romer model. So this seems to me like a pretty good time to take a little break. And then I want to kind of come back and talk about, well, then what does this mean, right? What does this mean about why rich countries are rich, poor countries are poor? What are all the implications of this, all right? And so, yeah, let's take a relatively short break here. How about 9:55 or so? We'll come back and we'll jump back in and talk about this, okay? All right, so see you in about 5 minutes or so. All right, everyone. Okay. Before we get started again, we're going to do a which would you choose? All right. All right. So I'm going to break you into small groups here, and you are going to discuss this very important question, right? Which would you choose? Hiccups whenever you speak in public, or giggles whenever you try to say something serious? Okay. Hiccups whenever you try to speak in public, or giggles whenever you try to say something serious. Discuss amongst yourselves, and then we'll come back and we'll have a group report. All right. Here's your breakout room. All right, what's the word? Who voted for hiccups?
Oh,
All right, quite a few of you. And who voted for laughing?
there we go.
Oh, this is a 50-50. Brahm, why did you go with laughing? Isn't like having people laugh at you when you're trying to say serious like the worst thing in the world?
I don't know. I just thought that I don't know, hiccups every single time you try and talk in public just sounded awful. So
Yeah, I have to say I'm not a person that gets hiccups very often. So, but I do know people. Have you heard about this poor guy? There's some guy, I think he's in Australia, that has had hiccups for like 20 years. I mean, the poor bastard, right? You thought your 2020 was bad. How about 20 years of having hiccups? Jesus. But so, Robin, you went with the hiccups.
No, I went for laughing.
You went for laughing. So isn't that embarrassing when you try to say something serious and people laugh at you?
I think laughing is at least a positive thing. Hiccuping is just kind of, I think everyone gets irritated by it. I don't think it's very charming to get hiccuped at all the time or to be hiccuping all the time.
Right. I guess so. You think it doesn't make any difference whether they're laughing with you or at you as long as they're laughing. Okay, I can kind of see that. So, all right. Well, on to less philosophical, maybe less important things. Let's talk about what all this means, right? What are the implications of the Romer model here? And so I think maybe the easiest way to kind of think about the implications is let's just kind of work through a couple of examples. Here we come. All right. So let's work through some examples or experiments in the Romer model. Okay. So number one, first experiment. Let's talk about a one-time increase in the population. We did this experiment in the Solow model yesterday. Let's talk about how it looks different in the Romer model. Okay. So let's think about what this looks like. Here we have time. And here we have per capita output. And let's make this a ratio scale. Right? So it's a little bit easier to see what's going on. So in other words, what happens to per capita output? It's going up linearly on a ratio scale. And then at this time, we have an increase in L bar. What happens in our model? Well, we know if there hadn't been a change in output, shoot, sorry, I tried to get fancy, and now it's not working, right? We know that if there hadn't been a change in output, that output would have kept on going up at this constant rate. What happens now that we have a change in output? Well, now that we have now that we have a change in labor. Now that we have a change in labor, if you remember what we talked about a minute ago, an increase in L bar leads to an increase in G bar, right? L bar is one of the components to G. And so what happens here is we begin to grow faster. We begin to grow faster. So in the short run and the long run, grow faster and we're richer. Okay. So once again, let's compare this and contrast this with the Romer. I'm sorry, with Solow. In Solow, an increase in L-bar led to a reduction in per capita output. Why? Diminishing marginal returns to labor. So in the Solow model, remember, it increased the size of the pie, right? So it increased, I can squeeze this in here, it increased aggregate output, but it reduced per capita output. And the reason was because of diminishing marginal returns. So yes, when you added more people, it did increase output, but the increase in output was smaller than previous increases in output because of diminishing marginal returns. This was the Malthusian result. That when you see your population go up, you get poorer over time in per capita terms, right? And so this is what Malthus worried about in terms of population, right? He was worried that, he was worried, sorry, I lost my screen. There it is. I apologize. Something funky happened on my end. There we go. So Malthus was worried that as the population got bigger and bigger, we have more and more people, but with the same amount of capital, right? Particularly land. And so he was worried that as population got bigger, we get poorer and poorer in per capita terms, right? And eventually, we basically starve ourselves, right? Of course, the good thing about starvation is that it would reduce the population and would actually make us richer, right? So, you know, this is a pretty dark view of the world in which the only way you get richer in the Malthusian world is to starve people, right? That's a pretty tough economic development strategy. We get something much different here in Romer. In Romer, an increase in the number of people leads to an increase in per capita output. And why? Because we get more ideas. More people means more ideas. Which of these views of the world match the best with the data? I don't think there's any doubt about it. It's Romer, right? As the world has gotten bigger and bigger and bigger in terms of population, what's happened to per capita GDP? It's gotten bigger and bigger and bigger, right? I don't think there's really any serious economist out there that thinks that the best way to get rich is to try to keep your country as small as possible, right? Having more people creates economies of scale in the terms of ideas, right? And so this is one of the reasons why, as we've gotten more and more people, we haven't had this Malthusian crash that many people have warned about. In fact, we've gotten richer because as we have more people, we're able to create new ideas. And so this application doesn't just apply to population growth, it actually applies to immigration, right? I mean, I think probably the most persuasive argument for a open immigration policy is simply this, that when you open up immigration, you get more people, you're also more likely to create ideas that benefit everybody, not just the person arriving in the country, but all the people who are already there, right? And you can probably think about this in terms of all the examples. What is it that I read? That 40% of Fortune 500 companies are either run by immigrants or the children of immigrants, right? It goes to show you that people who are creating ideas, right? Immigration is a powerful, powerful tool for creating new ideas, right? And so, yeah, you know, I think this Romer model in many ways provides a very, very strong explanation for why having more people and why having more migration actually is a policy for developing more quickly and growing faster. Let's look at a second example here. What happens if you spend more on research and development? Right? What happens if you spend more on research and development? How do we do that in this model? We increase little L bar, right? In other words, we increase the number of people who are working at producing ideas. Of course, when you do this, notice you're also doing this, right? So we're going to increase the number of people who make ideas, but we're also going to reduce the number of people who are making output. Okay, so let's graph this. Once again, let's put this on a ratio scale and make it linear and kind of easier to see. So here we have per capita output. It's going up at a constant rate. And then at this point in time, we increase L bar. Okay, what's going to happen here? What's going to happen first off to our growth rate? Well, remember what our growth rate is. It's that. So if we devote more people to research and development, what's going to happen to G? G is going to go up. We're going to grow faster. However, that's not the whole story here. There's another problem. When we increase L bar, that's going to reduce per capita output in the short run. Because remember what per capita output is. Right? If you increase L bar, this is going to go down and reduce output in the short run. So we actually have two effects here. One effect is on the growth rate over time, but the other is an immediate effect. And so what does this graph look like? It's going to look like this, right? Where right off the bat, right, initially we have a drop in output because now we don't have nearly as many people producing output. We have more people that are being devoted to research and development. That leads to lower standards of living for a period of time, but you see in the long run, it's actually going to lead to higher standards of living once we get the growth benefits of having more research and development and more ideas. So output falls in the short run, but it rises in the long run. Okay? So once again, this is a more complicated view of the world, right? A little bit more complicated view of the world than we saw in Romer. I'm sorry, than we saw in Solow, where spending more on research and development is not unambiguously a good thing. There is a cost to it, right? Because the more that we spend training scientists and technicians, the less people we have to actually make the things that we want to consume, right? And so the Solow model can kind of capture that, or I'm sorry, the Romer model can capture that trade-off. Okay, the third example I want to talk about. Let me just talk here about whether we have convergence or divergence in the Romer model. Does the Romer model predict convergence or divergence? Does the Romer model predict that poor countries should grow faster than rich countries and catch up? Or does the Romer model predict that poor countries should grow slower than rich countries and fall further behind? Well, here we have a pretty clear prediction in the Romer model. The Romer model predicts divergence. Why? Because why are poor countries poor? They have lower A. They have lower productivity. So if you have a low A today, it means that you have slower growth. And this leads to slower growth in the future. So this all comes back to what we talked about is really the critical aspect of this Romer model. Where do ideas come from? Having ideas. The more ideas you have, the more ideas you will create. Right? Let me say it again. The more ideas you have, the more ideas you create. What that essentially means is that the rich get richer and the poor get poorer, right? They have a high stock of ideas, and so the rich will get richer. And the poor will get relatively poor. So another way that you could think about this is that in the Romer model, there is a great deal of path dependence. And what I mean by that is where you are today really determines where you're going to be in the future. So if you're poor today and you have very few ideas, there's really in this model not very many ways. In this model, there's no way that you can kind of catch up in terms of ideas. So if you're poor today, you're going to stay poor in the future because you need ideas to create new ideas that grow faster. Likewise, if you're rich and you have a big stock of ideas, you will create more ideas and you'll grow faster. And if you're rich, you stay rich, right? So the Romer model here predicts a great deal of divergence, that the rich countries really get rich and the poor countries really stay poor. And so, you know, how do you explain things like a growth miracle? Right? Where poor countries catch up. How do you explain that in this model? Well, not really in this Romer model, right? There's really no way to it. I don't think, not a persuasive way to explain growth miracles in this model. However, it is possible to think about how you could change this model to possibly incorporate the possibility of growth miracles. For instance, one thing that you could add to this model is you could add technology transfer. What if poor countries can borrow the technology of rich countries? That might be a possibility. Right? Or it's possible that some countries could do a big push in R&D to try to catch up that way. But that's very difficult, right? Because as we talked about just a minute ago, the more you spend on research and development, the less you have for output. And in a poor country, you don't usually have a lot of output and a lot of income to spare. But to go back to the main point that I want to make, the Romer model strongly predicts divergence, right? This is a contrast. Oops. With the Solow model that predicted convergence because of diminishing marginal returns. So the Solow model strongly predicts convergence because of diminishing marginal returns. That's the key, the driving aspect in the Solow model. But in the Romer model, diminishing marginal returns aren't nearly as important, right? The key in the Romer model is leaks and matches, right? And so that's why you get such a different prediction between these two models. Which one is more consistent with what we observe in the real world? Well, here, I'll have to say, I don't know. I'm not sure that either of them is more consistent, because as we've talked about, if we look at the world, we see both convergence and divergence happening at the same time. So if the two countries that you're talking about are the United States and Kenya, I actually think the Romer model probably explains a lot more about what's going on, right? Because between those countries, we have divergence. And the Romer model, I think, captures a lot of why we have such strong divergence between the US and Kenya, right? US is creating lots of ideas and growing. Kenya is not producing very many ideas and has relatively stagnant per capita GDP. On the flip side, if you're talking about two countries that are very similar, such as the US and Canada, well then, yeah, the Solow model, which predicts convergence, is probably at least as insightful, right? And so, once again, I think, to really kind of understand what's going on in the world, you need to understand Solow, but you also need to understand Romer, right? You need to kind of keep both of these models in your head to understand that, yes, there are forces that drive convergence, but there's also some very strong forces that drive divergence, okay? All right, let's talk a little bit about extensions of the Romer model. Right, our model is very simple. Are there things that we could do or add to this model that would make it, a little bit more realistic or capture some things that are possibly getting missed? Yeah, and let's just kind of really briefly talk about two ways that you could change this model, right? And maybe possibly make it a little bit more realistic. One is we could add diminishing marginal returns to ideas. Here in the simple model that we work through, if you have an idea, it always increases productivity by the same amount. But maybe what's true about capital is the same as ideas. As we create more and more ideas, maybe new ideas have less of a benefit than the first ideas, right? So let me give you a more concrete example to talk about what I'm saying here. Let's think about the history of ideas, right? Let's go back to think about the creation of the wheel, right? There's an idea. What impact did that have on our productivity? Very, very high, right? Very, very high productivity. How about the creation of the internal combustion engine? Very, very high productivity, right? How about the creation of germ theory and sanitation systems? Very high productivity, right? Very big changes in productivity. How about the creation of social media? I mean, listen, I'm not saying that it does not increase productivity, right? But I think that I think sometimes we get lost. For people who think that Google is just as an important invention as the creation of the toilet, aren't really quite understanding human history very well, right? I mean, the creation of sanitation in the toilet was a huge boon to productivity, in part because it kept people from living in their own filth and getting sick all the time, right? So while Google has definitely increased productivity, I think you can make an argument, I'm kind of picking an extreme example here, but I think you could make an argument that a lot of inventions and new ideas, while they increase productivity, are probably not as likely to increase productivity as much as the first ideas. So how would this look, right? How would a production function that had diminishing marginal returns to ideas look? Well, I think it'd actually be pretty simple to incorporate this into our model. And all we would have to do is make this one small change. Here was our production function for ideas before. All we would have to do is, instead of having a coefficient on 1 here, make it a coefficient less than 1. Make it a coefficient of 3/4 or 1/2, right? By changing this numerically, what happens is that an increase in A does lead to an increase in A, the change in A. But at a smaller rate as the level of AT rises, right? So to think about this in another way, okay? Let's go back to this graph of a ratio scale. And then let's say there was something, let's say we increased L bar, right? We spent more money on research and development. How did this graph look before? Before, in our simple Romer model, we just grew faster forever, right? There's just a kink. Now, how would it look? Now, it would actually look like this. I'm getting my graph complicated. Okay. So if you can see this, hopefully you can see what I'm saying, but notice how you grow faster in the short run. Right? For a period of time, you grow faster in the short run, but what happens in the long run? Notice that the slope of these curves eventually begin to approach each other. And in the long run, you grow at the same rate as you did before, okay? So you grow faster in the short run, and that increases the level of per capita output, right? But it doesn't permanently increase the growth rate. And that might actually be probably a better way to think about the importance of ideas, right? Because we have not seen growth go up and up and up and up and up. When you have a great new idea, such as creation of information technology, or actually, let's go back. Let me pick another example, which we have more data on. Electrification, all right? The electrification of factories and houses. We have a lot of data on this in the United States, that this is a process that increased productivity, right? But it only increased growth for a period of time. Now, this is a relatively long period of time, for about 40 years, because it basically took about 40 years for the US to electrify all factories and homes, right? In that process, it led to higher growth. In the long run, it hasn't led to higher growth, right? We know this because growth in the US has been constant. But it did lead to higher standards of living because we grew faster for short periods of time because of it. And so that might be a better way of thinking about how technology and new ideas impact growth. That they impact growth in the short run But in the long run, we tend to come back to that balanced growth path, right? That kind of long run average rate of growth. Let's talk about another example here, or another way that you could possibly change this model. What if you added capital? Right? Notice that we did not use capital here in this model. What happens if you added capital to the Romer model? If you did this, what you would essentially get is a Solow plus Romer model, right? You get a model that includes the insights of Solow and the insights of Romer. And this is exactly what your book does in the appendix. And so for those of you who want to take a closer look at this, I would encourage you to take a look at the appendix. I'm not really going to work through the mechanics of it, but I do think it's worth us talking a little bit about intuitively what happens. And really, intuitively, what happens is that you get transitional dynamics. But this time, you don't get a transitional dynamics around a steady state. You get it around a balanced growth path. So in other words, in this model, you can grow greater or less than G bar in the short run, depending upon where you are relative to your balanced growth path. But in the long run, you grow at G bar. So in other words, what you get here is you get a little bit more complicated transitional path, right? So if I could, maybe a graph will help explain what the difference would be. Let's look at this graph that I just drew up here, where we had an increase in L bar, right? How would this look different? Before, well, I won't slide up to it, but before when we did this, we just had that kink. Right, we just had that kink. Now, how does it look different? Now you have to think about that we kind of ease into it. Instead of just having two straight lines, these are straight lines, by the way, it's hard to tell with my drawing. But instead of having two straight lines, what happens is we get this, where we grow slowly. I don't know if I'm really doing this very well, but we transition slowly up to the growth path, right? We transition. Yeah, I should have made this a little bit more clear. But the key is you transition to the new faster growth rate. It doesn't happen all at once, but you transition there. And why do you have that transition? Because you have to build up the new capital, right? It takes time to build up the new capital. So these are just a couple of ways that you can think about changing the Romer model. And yeah, and I mean, I think this is exactly how economists go about thinking about models, right? Is we take existing models and we think, what can this model help us understand? What can't it help us understand? How might we change this model to help us understand something that the model is not helping us understand, right? How might we tweak it? So I will say to you that I love these kind of questions on exams, right? Right? Because these are the kind of questions that are really asking you to think about things like an economist, right? So give you a model and say, hey, I'm going to tweak something here. How do the results change, right? What are the implications of this change, right? Think through them. How is it different than what we talked about in class, right? Just like I love to ask questions, compare and contrast this model to that model, right? So you notice a lot of what I've talked about here in the last 45 minutes is how does the Romer model compare to the Solow model, right? Thinking in terms of models, that's what economists do. And so, you know, this would be one of the things as you think about this weekend and you prepare for the exam, that I would encourage you to think about this in your own studying, right? Is, you know, here's a set of notes where we're talking about the Solow model. Well, here's a conclusion from the Solow model. How does this compare or contrast to the simple model or the Romer model, right? Or how might this change if I change this or if I change that, right? So a lot of the lectures that I've done here really kind of we've worked together about these kind of compare and contrast questions, or about how let's tweak the model, how do our results change, right? Because that's how you go thinking about questions in terms of models. And so I'm definitely going to ask you to do a little bit of that, maybe a lot of that on the exam on Wednesday, right? And so, you know, as you go back this weekend and you think about studying your notes, I'm going to ask you to kind of keep those questions at the forefront of your mind, right? Because that's a really good way to kind of make sure that you're really getting at what it means to think like an economist, right? And once again, to think like an economist means to think in terms of models, to compare and contrast in terms of models, to think about how if I change this in the model, I might get a different result. And then also to think about how does the model match the data, right? How does the model match the data? Where is it able to match the data and help us understand the world? What are its shortcomings, right? And if there's a shortcoming, is there something we can do to help it match the world a little bit better? Okay, so I think I'm gonna let off there, right? We just have a few more minutes. And so there's just one more topic that I want to talk about in chapter 6, which is growth accounting, right? Just the last couple of pages of chapter 6. So this afternoon at 12:30, we will meet. I hope this will be a pretty short afternoon class. We'll talk about growth accounting. We will talk about homework number 1, right? So I'll go and spend a few minutes reviewing it. I'll probably go through it pretty quickly, but please, if you have questions about homework number 1, ask them and we'll slow down and spend more time on any things that you have questions. And then we'll save a little bit of time if any of you have questions about looking forward to homework number 2, okay? All right, have a good lunch. We'll see you at 12:30.